Hello everyone, I'm Yali Jia from KCI Institute, Oregon Health and Science University. I want to use this opportunity to thank UG for hosting second IOCS conference during this challenging time, and thank Amani for programming these amazing sections. In the following presentation, I will talk about an automated DR classification method based on OCT and OCTA. Diabetic retinopathy, DR, is the principal cause of vision loss. The diabetes-related vision loss can be prevented if DR can be screened timely. The gold standard method to detect DR is based on manual grading of color founders photography in 7 fields, defined by ETDRS group. But this assessment requires highly skilled readers, which is very labor-intensive and costly. From the perspective of a patient, taking 7 fields is time-consuming, tedious, and uncomfortable. So, many automated algorithms have been developed to detect DR lesions and provide a DR severity grade. Based on that, they can give referable, non-referable DR recommendation. With the advance of AI, deep learning has been used to assist DR detection. So far, the main output focuses on referable DR versus non-referable DR, no DR versus DR. Founder's photo is two-dimensional with much limitation on detecting diabetic macroedema, which is a severe condition of DR. So traditional structural OCT has been used to detect DME, recently with the help from deep learning. A computer assistant diagnostic system was also recently reported to detect NPDR based on structural OCT only. With the more extensive use of OCTA in clinic, it's very reasonable to consider using OCTA scans for DR detection. Last year, Dr. Yal's group proposed a support vector machine-based DR classification using 6 quantitative features generated from OCTA. Dr. Serenik group proposed a DR classification method based on on-fast OCT-OCTA using ensemble networks. Our group have been very diligent developing novel DR features based on OCTA. All of these features help us understand OCTA potentials in diagnosis of DR. So OCTA based on deep learning assisted DR detection is also our interest. In our work, we proposed a new deep learning network to detect DR at 3 classification levels in order to fulfill different clinical requests. A PhD student, Pengyao Zhang, led the network development. The ground truth was generated based on ETDRS grades of founder's photo in 7 fields. Due to the small number of cases in mild and moderate classes, they were combined in level 3. In level 2, all non-proliferative DR were combined. The first level, the cases with a score higher than 35 were put in referable category, and others were in non-referable. Here's the number for each group. In the whole dataset, we reserved the scans from 30 eyes used for independent and external testing. All other scans were divided into 10 subsets, and 1 subset was dropped from training and used for testing. So 10-fold cross-validation was performed in this study. All OCTA scanned 3 by 3 mm acquired by Avanti RT-View XR at center macular. 6 types of en-face images were used as input channels. They are inner retina thickness map, the mean projection of reflectance of inner retina, and EZ, and the 3 retinal capillary plexuses, superficial, intermediate, and deep. There are 2 major challenges. OCTA data is very complex, and also the number of available dataset is small. These challenges can lead to a very severe slow convergence and overfitting problem for this network architecture. To overcome these problems, we designed a novel neural network. The first idea is we borrowed dense connection concept from DenseNet. In DenseNet, the dense connection was only used within each dense block. In our network, the dense connection was continuously used in the whole network to further improve the information flow. This is very important for improved convergence. The second idea is we applied a dropout rate in bottleneck block and an adaptive dropout rate in transfer block to reduce overfitting. The third idea is we applied adaptive label smoothing to modify a loss function. Here is cross entropy loss in our study. Crowding to this loss function, further reducing the loss value, cannot further improve the detection accuracy. So we adopted label smoothing concept. This modification can provide a tighter clustering and a greater separation between categories. In our network, we integrate all these solutions to improve converging speed and reduce overfitting and overconfidence. We evaluated the overall prediction accuracy, which is the number of correctly predicted cases divided by the number of whole dataset, and found the best accuracy is on 2 class level. This 95.7% accuracy is comparable to the reported accuracy based on founder's photo. We also noticed that the sensitivity on detecting severe NPDR is quite low. There are 2 reasons. First, the differences between moderate NPDR and severe NPDR is very small. Second, the number of severe NPDR scans is quite small. This network can also produce class activation map, which can be used to visualize features that are important for decision making. Here are the en-face images we input to the network. The heat map overlay shows the areas network considered important for diagnosing DR in red. They are mainly the regions with features of fluid and non-perfusion areas. Class activation map can also shed light on discovering new biomarkers previously unknown to us. Take-home message. First, we developed an automated framework for the DR classification based on both OCT and OCTA data at 3 DR classification levels. This network architecture is based on a couple of novel ideas to overcome the challenges of slow convergence and overfitting. Our study also shows OCTA is sufficient to diagnose DR at the level similar to founder's photo. So in the future, we might want to consider OCTA for DR staging. I want to acknowledge the grant support from NIH RPB Bright Focus Foundation, and material support from OptView. And I want to acknowledge the co-author team and the great support from Retina Service at UC and our cool lab whole member team. Thank you for your listening.